Hello and welcome to this physics guide to go through ammeters, voltmeters and more resistors. It is a work solutions guide where we'll see the questions in the exercise sheet and have a go at working them out and working them out in full detail. So without further ado, let's take a look at this set of questions here, 23 all the way to 26. I split my page here or screen into quarters, and that's the way that I work through it. So for example here, 23, where we've got 16 and 8 ohms. Now, these 16 and 8 ohms, they are in parallel. Now, considering that they are in parallel, what we're going to do is use the key equation for resistance in parallel. So we use this equation here, which is 1 over R total is 1 over R1 plus 1 over R2 plus ... Now we've only actually got two resistors here, which are in parallel, so all that I actually need to do in terms of laying out my equation here is just go with 1 over R total. The reason why we're doing 1 over R total is because it says calculate the total resistance. And in this case, it's going to be 1 over 16 ohms plus 1 over 8 ohms. Now, if you actually do 1 over 16 plus 1 over 8 in your calculator, you should end up with something that looks like this, which is going to be 3 over 16. Now that's 1 over R total. We want the actual R total. So what we've essentially got to do is do 1 divided by everything, or essentially invert it. So if we get the inverse here, all that we really end up with is R total. R total is 16 over 3, and don't forget that has units, which are ohms. You could write out ohms, OHMS, or you could just put the ohm symbol. It's really up to you. 24 over here, this time what we've got is a pretty interesting combination of resistors in this branch here. I'm just going to call this one branch 1, and I call this guys over here branch 2. So we've got branch 1 and branch 2. Now, we've got 2 in series, essentially in branch 1, and 2 resistors in series, essentially in branch 2. So the first thing that we should actually do is have a look at the total resistance of branch 1. So branch 1, what we've really got is we've got resistance of 8 ohms plus 8 ohms, meaning that branch 1 itself has an overall resistance of 16 ohms. If you imagine current going through branch 1, it's got to go through the 8 ohms, and it's got to go through the 8 ohms. Essentially, it's gone through 16 ohms worth of resistors. Do the same thing for branch 2, and what we've got this time is 14 ohms plus 2 ohms, which is 16 ohms. Anyway, so what we then want to do is, now we've got essentially two 16 ohm resistors. That's the equivalent of what we've got in parallel. So what we do now is we go to our parallel equation, 1 over R total. I won't write out the whole thing because it's there. And we just do 1 over 16 ohms plus 1 over 16 ohms. And that'll give you 2 over 16 ohms. Again, that's 1 over our total. We want our total, not just 1 over. So we do the inverse, and what we end up with is 16 over 2 ohms, which is otherwise known as just 8 ohms. And that's your answer there. Go and tick these. You can check your answers, of course. Start a point in this. 25. Well, 25 here is just 3 resistors in series. Yeah, I'm being series there. Series. Anyway, so you have 3 resistors in series, 4 ohms plus 8 ohms plus 16 ohms. Again, imagine you're an electron, you're trying to go through the circuit, you've got to go through all 3 of those resistors. You would have gone through, in that case, 4 plus 8 is 12, plus the 16, you've got 28 ohms of resistance there. That's our total. I guess I could say our total there. So that's that one done. And then 26, again, you can just see here there's 3 resistors in parallel, low. So what do we do this time? Well, pretty much the same as before. We're just going to use our 1 over our total. We're going to write out the whole thing because it's up there. And I'll just say here, go 1 over 16 ohms plus 1 over 8 ohms plus 1 over 4 ohms, which if we add all those up, we end up with, and this is where calculator is extremely useful, but you'd end up with, in this case, 1 over 16 plus 2 over 16 plus 4 over 16, which is 7 over 16. But again, that's 1 over our total. We want just our total. So you're going to invert it again. And what we end up with is our total equals 16 over 7 ohms. So that's those 4 questions done. We have a look at the next set of questions here. Okay, let's first of all just read through the question carefully here. It says here, find the ammeter. That's not very useful. Try that again. Find the ammeter and voltmeter readings in the circuits here, 27, 28, 29, 30. It does say here, and this is super important, all meters are ideal. The batteries have no internal resistance. So we don't need to worry about non-ideal voltmeters and ammeters and so on within this question. So what we've got is start with 27, go in order here, 27, we've got 6 volts. 6 volts is our source potential difference, or essentially our EMF, but we'll do a bit more on that later in this course if you haven't heard of that before. So 6 volts is essentially our EMF, our source potential difference there. And we've got here a 10 ohm resistor, a 2 ohm resistor. There's a voltmeter in the 10 ohm resistor, there's an ammeter for the whole circuit. It's a series circuit, I'm just going to note that here. This is series, and that means that the current at any point is going to be the same. You see this little arrow here in the circuit, that's just showing the conventional current, positive to negative. Remember that the actual electron flow is negative to positive, but conventional current, the old way, positive to negative. So we see here we've got 6 volts, and I said 10 and 2. So the first thing actually that I'm going to do is just work out what is my total resistance. Well, it's in series, so all I've actually got to do is 10 ohms plus 2 ohms, and that gives me 12 ohms. That's my total resistance. That's not actually answered the question, but it's getting me there. It's closer. Because what I can now do, remember, Ohm's law, we can use that equation for Ohm's law, which is V equals I times R. In this case, if I want to know the current, what I'm going to do is just say I equals V over R. Well, I know the total potential difference here is 6 volts. I know the total resistance here is 12 ohms, so I know that the current is 0.5 amps. That's actually one of my answers for 27. What I can then go and do is try and work out what is the potential difference across the 10 ohm resistor. Well, I know that V equals IR. I know that the current, how have I done that? How do you, there we go. Redo that bit. I know V equals IR, and I've got current there, which is 0.5 amps. I know the resistance is 10 ohms. So what I really need to do here is V equals 0.5 amps times 10 ohms. This will give me the potential difference just across this resistor, which is 5 volts. Job done. 27's over. Go to 28. 28, again, pretty interesting here because what you've got is overall a parallel circuit. Now I'm going to refer to this as branch 1. I'm going to refer to this as branch 2. That's this whole thing. Okay, so what we want to do this time is have a look at branch 1. Branch 1 is just 4 ohms. Branch 2 is 2 and 2 ohms. So actually the first thing for me to do is have a look at branch 2 for branch 2, the total resistance is actually 2 ohms plus 2 ohms. That symbol's getting a bit janky there, but let's do that again. 2 ohms, it doesn't really matter as long as it looks like ohms. 4 ohms total. So what I've really got is the equivalent of 4 ohms in branch 2. That's super useful. Now it's a parallel circuit. It's a parallel circuit. So what I can do here is now employ that equation. 1 over R total equals 1 over 4 ohms plus 1 over 4 ohms, which is 2 over 4 ohms, which means that my R total, not 2 over 4, but is actually 4 over 2 ohms, which is, well, otherwise known as 2 ohms. That's the total resistance within this circuit. I'm going to use Ohm's law equation here and just do it for I. So I equals V over R. We know that we've got 6 volts in total. So I'm just going to put 6 volts over 2 ohms, which gives me 3 amps. That's actually one of my answers. The next bit is to work out what is this voltmeter reading here. So for that voltmeter reading over there, I'm just going to use V equals I times R. Now one thing to watch out for is if there's 3 amps here, when we go down this branch, there's going to be 1.5 amps. When we go down this branch, it's 1.5 amps. How do we know that? Because the equivalent resistance for both those branches is the same. Pretty useful. It's 4 ohms equivalent for branch 1 and branch 2. So the current will split evenly. So now when carrying out V equals IR, I know that through this whole branch, branch 2, there's actually 1.5 amps. So for V equals IR, all I'm going to do is 1.5 amps times by 2 ohms, which gives me 3 volts. That's 3 volts going through the 2 ohms. That means this thing here will be 3 volts. And I can tick that. There are other ways you could answer that question as well, because you know, for example here, that if that's 6 volts, then branch 1 is also going to have 6 volts across it, and branch 2 is also going to have 6 volts across it. Because these two resistors, 2 ohms and 2 ohms, are the same, that 6 volts is spread out evenly across each resistor. There's a voltage drop that's the same across each resistor. 6 volts divided by 2 is 3 volts. So that's another way of getting to that answer. So have a look at 29. Pretty much the same thing, but this time we want to know the voltage across the 4 ohms, and we want to know the current over here. Well, actually, I'm not going to go through all of the working again. It's the same circuit as last time. You can use the same working to work out that it's 1.5 amps for here. That's 1.5 amps. Give that a tick. And over here, because we know it's 6 volts from our cell, we're going to have 6 volts across branch 1, 6 volts across branch 2. Well, that means the 4 ohm resistor gets all of the 6 volts. I'm just going to tick that. Last one here is 30. Now, with 30 here, actually a lot of it is pretty similar again. Let's talk about why. So we've got a 4 ohm resistor and a 4 ohm resistor. We've got branch 1 and branch 2. Remember how the equivalent voltage for these two resistors on the left and 29, 28 gave us 4 ohms, because we could just add them, and that means that the R total was actually just 2 ohms plus 2 ohms, 4 ohms for branch 2. So actually it's really similar, and that means that the overall current here is going to be 3 amps again. And if you're not sure, you can just kind of look back at this one here where we worked out the R total. When you've got 4 ohms and 4 ohms, gives you 2 over 4, which is R total of 4 over 2, which is 2 ohms. And if you have 2 ohms, then again, I equals V over R is 6 volts over 3 amps equals 2 ohms. What have I done there? There we go. I meant to put here 2 ohms, okay, is 3 amps. That's where that 3 amps comes from. In terms of the voltage here, so you can just tick that. In terms of the voltage here, that's just measuring across the 6 volt cell, which we know is 6 volts. So that's just going to be 6 volts. So the voltage is 6 volts. Tick that. We'll have a look at 31 next, which is the non-ideal meters. All right, let's check out this last one here, which is 31. So we've got here meters that are not ideal. They're not ideal because the resistance of this voltmeter is nowhere near as high as they often are. Typically, ideal voltmeters have a resistance between kind of 10 to the 7 and 10 to the 9 ohms. 10 to the 7, 10 to the 9 ohms, you're really talking about, in this case, kind of 10 mega ohms to sort of 1 gigaohm. That's the kind of range we're looking at. It's pretty high. This is only 2 kilo ohms, and that's actually really close to the 1 kilo ohm. So that means that this voltmeter will actually allow some of the current to go through it, and that affects the overall circuit. Some of the current's actually going to be diverted through, I'm going in the conventional current direction, through the voltmeter. It's actually going to end up going that way and then joining up again. So we've got to sort of take it into account. So let's look at what the question's demanding. It says calculate the potential difference across the second resistor with and without the voltmeter in this figure. Once we've got that, we then need to just work out the percentage difference between the readings. So imagine that voltmeter was not there. If we go with kind of part 1, breaks into parts, part 1, without the voltmeter, well then you might go, how would we know what the voltage is? Fine, we'll just calculate it. So without the voltmeter, what sort of reading could we get? Is we could take a look. So we've got 6 volts, remember that, from our source, from our cell, and there's 2 identical resistors here. Oh, I've done that again. 1 kilo ohm and 1 kilo ohm. So what we want to do is, without the voltmeter, you'd essentially have 6 volts divided by 2, which is 3 volts. There'd be 3 volts drop here and 3 volts drop here. 3 volts for each of them. That's without the voltmeter present. Now we've got to do part 2, which is the more involved one. Part 2 is with the non-ideal voltmeter. That's what we've got to do here. So this time we can essentially treat this as just another resistor. It's another resistor, and it's in parallel with the 1 kilo ohm. So I'm just going to draw a little ring around it. In fact, I'm going to draw a ring around it in what I thought was going to be a different color. I can't seem to. Oh, there we go. I'm just going to draw a ring around it in a different color to show that actually this is going to behave as one thing. It's like 2 resistors in parallel across that. So what we've got to actually do this time, let me change back, is we want to work out what is the equivalent resistance, in other words, the R total of the 1 kilo ohm resistor and the 2 kilo ohm voltmeter. I'm going to be referring to this as just the R total. So what we've really got, in fact, I guess I should go with R total parallel, something like that. R total P. Go with that. So what we've really got then is we're going to use that equation again, 1 over R total. This time I'm just going to put R total P, because it's just for that green combination. And that's going to give us 1 over 1. That's kilo ohms. So I could put 1,000 if we wanted to. Maybe we should. 1 over 1,000. ohms, that is, plus, not equal, plus 1 over 2000, because that's 2 kiloohms. Now if we add those up, what we actually end up with is 3 over 2000 ohms. So that means that our actual, because we don't want 1 over our total P, we want our total P is actually 2000 over 3 ohms. Pretty useful. You'll see why, because now what we can do is, if we know this whole combination thing, and let me see if I can stick with that color change there, that thing is worth 2000 over 3 ohms together. Remember, that's our total P. Then what we can now work out is the actual total resistance for this entire circuit, because that our total P is also in series with this 1 kiloohm. So what we now want to do is the full R total. Notice I'm not writing R total P this time. Our total is going to be 1000 ohms plus 2000 over 3 ohms, which is going to give us this one. We'll need a calculator. So we've got here 1666.6 occurring. I'm just going to write that out as 1667 ohms for now. It should be precise enough. If you can carry it through, obviously do a little bit limited at the moment with equipment. So what we want to do next is to work out the current in our circuit. And again, you might be thinking, well, why? Why would you do that? And that's because if we can work out the current in the circuit, remember that the rest of the circuit is actually a series circuit. If we know what the current is, then we can work out, using V equals IR, the voltage drop for here, and, well, importantly, the voltage drop for here. And if we know that, then we know the voltage that we're going to get on that voltmeter reading through that parallel set of our total P. So now what I'm going to do is just use I equals V over R, and look back in the video if you're not sure about where that comes from. So just do 6 volts over 1667 ohms, and that'll give me 0.00359992 blah 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 amps. That's the current in our circuit. Now I want to know, what is the voltage drop going to be across the 2000 over 3 ohm resistance equivalent, R total P. So I'm just going to use V equals IR, and I'm going to do this equation here. So just going to put 0.00359992 blah 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 times by 2000. But not 2003. I'm just going to do that as 1667. And that'll give me a slightly awkward silence. Okay, well, I've kind of goofed that up a little bit, which shows that it's pretty easy to make mistakes at times. I'm using the R total there, which is wrong. I should be using R total P, because you want to know the voltage drop across R total P, that equivalent resistance. I did not need to get rid of that line. Let me finish this off before this drags on a bit. So yeah, let's just get this one done. So that should actually say, that correctly said 1667, because that is the total resistance for the circuit. It's just this last bit here. I want to work out the drop across our total P, which is 667 ohms, not 1667, because that was actually including this one, which was our total, not our total P. So if I do that, then my calculator says that I've got 2.400664, and so on, which I'm just going to say is 2.4 volts. So that's the voltmeter reading with the voltmeter. That's that bit done. This was that bit done, and the last part was to actually work out the percentage difference for with and without. So in order to do that, first thing I need to do is actually work out the difference. So it's going to be difference divided by original, essentially, is one way of doing it. So I'm just going to do this as follows. So 3 volts take away 2.4 volts divided by, in this case, the 3 volts, put into my calculator, and what we've got is 0.2, but because I want a percentage difference, I'm just going to times it by 100, and I get 20%. That's the last part of this question. And that is a review video done for this worksheet on ammeters, voltmeters, and more resistors. I hope that was helpful, but if you've got any questions, just get in touch and let me know. I'd be happy to help. Goodbye.